Okay, let's go for the next experiment. In this case, we have uniform circular motion, where we have an object moving a circular path of constant speed, right? When that happens, we have a force, right, acting on this object, right? And that force is the centripetal force. If the speed is constant, right, the net force is centripetal force, which is represented by m, right, a mass of the stopper in this case, times the velocity, right, divided by the radius of the circumference. Okay, the velocity, right, is represented in this way because it's in circular path, right? As we know, the speed or velocity in this case is the distance divided by the time, right? And the distance is the length of the circumference, and the formula for the circumference is 2 pi r. And this is the period because we expect, right, to be at constant velocity, so the time for one revolution is always the same, so it's periodic motion, so this is the period, right? Okay, now we have to plug, right, this value right here, this quantity right here, to find the centripetal force acting right in this motion. Okay, perfect. Now this experiment is done in this way. How we can measure also the centripetal force? Well, because the speed is constant, we attach, right, by the string, this stopper right here, right, another mass, and this mass is supposed to be at the same position when we make rotate, right, m1. When that happens, right, the speed is supposed to be constant, and we use this little thing right here as a reference, right? If we keep always that at the same distance from this tube, right, we expect at the same time, right, the velocity of the stopper to be constant. When that happens, well, we have to measure the time for one period, but it's hard to do it in one trial. To do better this experiment, we measure the time of 10 revolutions, right? 10 revolutions, and then we divide that time by 10 to have the time of one period, because that's the time that appears in this formula. Correct? Okay, great. Now, we have the masses for the stopper, for example. In this experiment, we have gonna be 0.0119 kilograms. For the mass for case one, we have two cases. Case one, 0.81 kilograms. Then we have to measure, right, the radius. The radius is gonna be, right, the distance from the center, right, of this tube to the center of the stopper. Correct? Okay, great. Also, we can calculate, right, the weight, right, for this object. It's gonna be, as you know, m, mass times gravity. The units are newtons. And the same thing, we can calculate, right, the centripetal force for case one when we are dealing, right, with this mass. Right? Okay, perfect. Then we substitute the values. This is given, right? Is this one. Velocity, right, of course, is substituted by 2 pi r, is also provided right here. And we have the time. The time is gonna be found in these two boxes, right? We have two cases for each case, two trials, right? For case one, let's make one trial, right, and find the time again for 10 revolutions, right? When we are counting revolutions, right, we use, right, we start from 0. For example, this is my reference point. So the stopper, in this case, this one is coming and passing through this, right, reference point. We can count all the way from 0, right? Then we say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? And we calculate the time using your cell phone. You can calculate that time, right, for 10 revolutions. Imagine that time is, let's say, 20 seconds. Imagine this is 20 seconds, the total time for 10 revolutions. What should be the period? In this case, well, we divide that by 10, gonna be, right, 2 seconds. We have another trial, right? Let's do it again to make sure that everything is correct. And imagine that the next one is gonna be 22 seconds for 10 trials. What should be then the time for the period? Well, should be, right, 2.2, right? It's an example. And then let's increase the mass, right? When we increase the mass, we increase, right, of course, the centripetal force. If we increase centripetal force means that we increase the speed, because we expect the radius to be constant, right? Because it's our reference point, right? So we expect the radius to be the same for both cases, but the time is gonna be not the same because we are changing, again, the weights right here, we change the weight, we're changing the centripetal force, we change centripetal force, right? We change the speed, right? Let's do it, let's try it today. Again, once we calculate the time, the period, please let's find the percent error. The percent error is gonna be, because we're comparing two quantities, right? This centripetal force will be equals to this weight, right? To this, to that weight. So let's do it this way. Let's use the weight of case one, right? Case one, weight 1 minus, right? The centripetal force, again, case one, perfect, divided by the average. Usually we use this average when we don't have a standard value, right? A quantity that we take as the true value or a standard value or the theoretical value. When we don't have that one, like in this case, we can use, right, for a good approximation, the average of these two quantities, and then multiply by 100% to find the percent error, correct? Also, let's do the same thing for case two. Again, calculate the weight, the centripetal force using the new mass, which is this one, is a different one, right? And then in the same way, let's calculate the percent error. I'm gonna show you how to do it. Okay, this is the device that we use in this experiment, right? So we are supposed to rotate the stopper, right? And let's take this masking tape, right, at the same position all the time, right? And we start counting. You can start at any time. I want to try to keep this distance always at the same position, right? And then you can start any time, right? The counting of 10 revolutions. Okay, so you start counting using your stopwatch and pay attention right here on the position while you are counting. Okay, remember we have two trials for each case to make sure that it works, right? So now so far I have like 20 or more revolutions. Again, you can start any time, right? As long as you have 20 revolutions, 10 revolutions actually, right? The time for 10 revolutions, and then you divide that by 10 to find the time for a period, correct? Okay, now let me start right here for case one, and let me attach another mass, right, to do case two, correct? Okay, I'll be back. Okay, this is case two, right? Case two, we add more mass, right? That represent M2 right here, or weight 2. Okay, let's do it. So we have, again, to repeat the experiment, let me keep, right, this distance constant as before, at the same position, and you can start any time, right, taking, oops, wait, not yet, okay, taking the time, right, for 10 revolutions. You can start now at any time. Okay, and pay attention again on the distance right here, must be about the same all the time, right? So you take again the time for 10 revolutions, right? For 10 revolutions, please hurry, okay, because this is not so easy to do. Okay, to keep again the same position all the time. I think I did it by myself, right? Let me see, looks fine, okay. Hopefully we have enough revolution for you for the time that we need, right? Okay, great. So let me start right here, and Now I'm gonna show you right the values for the radius and for the masses to make sure that everything is correct. Okay, perfect. Okay, so again we have the time for time oscillations, right, for case 2, another trial, right, again, and then divided that amount by 10, rather give us the time only for 1 revolution, which is the time for the period. Perfect. And the same thing, right, let's find the percent error. Please show all the values, show the formulas all the time, right, with the values, right, and the percent error. This is a good experiment, it works. This is a homemade experiment, right, you can do at home. You have a tube like this one, right, a tube, a string, and the masses, you know, the value for each mass, right? Well, you can do it anytime in your house, in your home, right? And you will see that it works. You need a stopwatch or your cell phone to do it, correct? And we have all the data right here, right? I'm gonna give you only the radius, which is gonna be the same for both. It's gonna be in meters, okay? And you need to report this right later and send it to me right later. Okay, thank you. Okay, let's go back to the measurements. Let's measure the radius, right, for this circular path. Okay, this is more or less the distance, right, that we use for the radius, right? It's gonna be this one. You can do it at home, right? It goes from this position, right? Let me adjust this part. Okay, it goes from this position to the center of the stopper, right? The center, as you can see, is right here, right? Or another way, this one, right, from the center, from this position, right, to the center of the stopper, right? You need to estimate more or less what is the center. Remember to take into account also the center of this tube, right? Because the radius goes from the center of the tube to the center, right, of the stopper. Got it? One more time. Okay, from here to here, right? To have an idea. Let me adjust it one more time. This is the best one. One more time. From here to there, right? Another way is right here. You approx, right, that distance. Again, from this position to the center of the stopper, plus, right, at the center of the tube. Is also given that the radius on the board. Okay, perfect. Now let's go to find the masses, right, for the objects that we use today. Okay, so today we use the stopper. We have this scale right here, right? The scale. Hopefully you can see, right, let me see if it works or not. Okay, what happens? It was working before. Okay, it's work. Okay, it works. Okay, perfect. Now it's in grams. Perfect. So this is the mass of the stopper. Oops. Right here, as you can see, it's 19, right? 19 grams. Perfect. Now let's find the mass of object mass 2 for case 1, right? Which is the body right here. So it's about 881. Okay, before it was 81, now it's 80. Okay, 881. It's okay. 1 gram is not a big difference. Okay, so this is for case 1, right? This is gonna be M2. Okay, let's go for case 2. We have all of these masses, correct? Is equals to 132 grams. Okay, let's use this data. It's also given on the board to calculate the centripetal force, right? The weight and the percent errors for this experiment. Okay, thank you.